Good morning, everyone.
Good morning.
Hopefully everybody got my emails from yesterday. Anybody have any questions while we're waiting for people to enter?
I had a couple questions just off of chapter 43 homework, but
Okay.
I guess I can wait until everybody's in.
Yeah, that might help since that is our current chapter. Let's wait to answer it till we get a few more people in at least. But what was I gonna say? So some of the things I want to mention to everybody is I am in the process of attempting to put up practice the last or maybe even two last practice tests. I'm leaning really towards just one last practice test for one last test. Obviously, if I put up two, that'd be two last tests. But the plan is we're definitely gonna have at least one more test that should cover 14, 15, 43, and 44. The reason why I considered two is maybe it'd be 14, 15, and then another one for 43 and 44. If I do one of, well, I will do one of them, and that one will up our dropped online tests to 2 instead of 1. If I do 2 of them, I may even make it to 3 instead of 2, but I'm not leaning towards that. So I'm definitely going to do one more test, and I'm going to try to have the practice test up by Friday of this week, which is tomorrow, of course. And I'm also trying to have the practice final exam up by Friday of this week. So that's something I'm attempting to do. Hopefully not. Hopefully I won't fail and not get that done, but I should be able to. I'm about done with the practice final, which I thought was more important, but I haven't done the practice test yet. So what I expect to happen is maybe I'll put up the actual tests Monday, or maybe even put them up this weekend and give you until like Sunday of next week. So that's the battle plan. If I'm able to give you this test, that includes 43 and 44, then my intent is to leave that off the final. I think that's new enough and stuff like that, where if I have one good test of it online, then I feel okay enough to let you go by with that. But then I'll leave it off the final, and we'll just have the typical 1 through 11, 14, 15, and then of course 36, which is relativity. So that's what the final exam will be on. All right, well, I guess we've only got 9 people here, but we don't have that big of a class to begin with. So I guess we can go ahead. I've actually invited all the other 241 classes to come here. So when I speak in vague terms, let's put it that way. I was trying to say vagaries, and I'm not sure that's right. But anyways, when I speak in vague terms, it's because of that. So for instance, just a reminder, you guys, our last week of classes is Monday the 13th through the 17th on Friday. The way I set it up is the final exam is supposed to be the next to the last day of class. So if you're a Monday, Wednesday, Friday class, which you guys I know are not, you're Tuesday, Thursday, the people for this lab. But if you're a Monday, Wednesday, Friday class, that means Wednesday will be the final exam. If you're a Monday, Wednesday class, that means Monday will be the final exam. That's the 13th again. And if you're a Tuesday, Thursday class, that means Tuesday will be the final exam. That means the 14th. So just want to reiterate that to everyone. We're doing it with a respondus test as normal. If you have a problem with that, you need to let me know immediately, like before Monday, because I'll have to set up something with the testing center for you to take it that way.
I would like to take it at the testing center.
You would? Okay, and this is Colby?
Yes, sir. Just the one at Chesapeake is would be
okay.
Best.
And you're in my D01C Physics 241 class. All right, I'll set that up for you, Colby. Thank you. I've got a note written here, so that should remind me, barring me just having a goofy stroke or something. So today, what the email will explain to you guys is we may or may not do a lab next week. We might just do the same thing, having our question and answer session, because I noticed we have a lot of students that did poorly on the midterm. And this final exam, I've told everybody, if you do better on this final exam, I'll replace your midterm grade with the final exam grade, but not the other way around. So I really want to make sure you guys have ample time to get all your questions answered and stuff like that. So I would ideally like you to, show up, not of course today, but also for any of the other labs, you can make it show up with actual questions, either questions, big questions like the concepts or how do we apply this or how do we apply that, or what does Newton's first law mean? What does Newton's second law mean? What's conservation momentum? What's conservation angular momentum? All that good stuff. So that's really what I'm shooting for you to ask, and ask physically, or really how to solve these physics problems. Here's a problem that I found in the end of chapter 3 of the textbook, and I was wondering how you'd solve that. And then of course I'm going to go to trying to solve it for you. Here's a homework problem that I didn't understand. Could you help me with that? Or here's 2 test problems that we had on past tests, or here's 2 practice test problems that we had on past tests. Could you help me with that? So all of those things are the types of stuff I look for, because I really want you guys to make sure you are at your peak performance on the final. And I make my finals comprehensive, one, because it's really good pedagogy. If you go back and review all the stuff you've covered in a given course at the end of a course, you actually retain it a little better than if you hadn't. So that's one good reason. The other good reason is I like to give my student a chance until literally the very last day. So if a student usually I don't allow it when you miss tests, but if you've missed a few homeworks, or even you just been good enough to do well without doing the homeworks, and you got to, of course, minus 20% because you didn't do any of the homeworks, then the best you can get is like an 80, right? And of course, you're likely not to get perfect 100, so maybe you're in the 70s now. If you go into the final in the 70 and you pull off a 98, say, on the final exam, that's not going to be enough to give you an A. And it's probably not even going to be enough to give you a B. But when I look at that and I say, okay, here's a student that took a comprehensive final exam in physics and scored a 97 or 98 on it, I'm not much inclined to let that student get a C. I'm probably going to give them at least a B and maybe even an A. But that also works for the student that has an F. The student that has an F comes in, pulls a 95 or a 97 or even an 85, 87, something like that. I'm not going to let them get that F, and I'm not going to let them get a D probably. Okay. Now, all that's out the window if I find something fishy where you on your video about you possibly looking in your lap at notes, or a computer of some sort, iPad or phone on the internet or something like that. If your video looks remotely fishy, I'm just going to assume that's not good. Okay. And last time I got a ton of warnings, so be careful with that, folks. Make sure you don't do a lot of this. I mean, if you're wanting to bend down and write stuff, make sure your computer camera is put right here so you can see what you're looking at. I want to see your head, your eyes, where they're at, and I want to make sure that you don't have anything in your lap. That's part of the reason why you're supposed to show your workspace and all that good stuff, and not supposed to leave the camera's eye. So please, please, please make sure I don't get anything fishy like that, because I sort of looked at all of them this time and didn't think anybody was really doing anything. There was a couple of cases where I thought maybe they could be, but I'm not going to be nearly as nice on this one. So make sure you stay on the up and up. No phones within your reach. A calculator that you have to have will be a calculator either on your computer, which I think I said it so you can do, but more specifically, you're supposed to have a scientific calculator that is not your phone. So make sure you have that. Notebooks. I did post a equation sheet on your Canvas page. So in the important links and documents, you can find an equation sheet that has all the equations from Gene Foley. You can have that whole sheet there, or all of those pages there. You can have that on the test. Of course, you're going to show it again front and back to the camera before you start up. But you can have all that, and any equations that I made up that aren't in the book, are ones specifically that were in the book but not numbered, and I told you can use, which I can't really remember any of that second category. But the first category, the way I solve conservation of energy problems, and the way I solve no, we didn't do that. Okay, the way I solve conservation of energy problems, you're allowed to write that on the equation sheet. Okay, so that's the generic stuff. And I think Colby had a question on chapter 43, so let's let him start with that. And I'm going to set it up so you can share the screen. Man, now all of a sudden my sinuses start hitting me.
Oh, actually, I'm not able to share my screen. I've always done this on my tablet.
Okay.
But I do have the question pulled up. It was under it was problem 8 part A on the chapter 43 homework.
Okay.
It said determine whether the following reactions and decays are possible. So they give you the pion minus plus a proton yields a neutron and the eta 0.
The eta, that's the, is that the one that looks like a N?
Yeah, it's like the squiggly N. Yes, sir.
Okay. And plus, so I got the neutron plus the eta. You say the eta 0?
Yes, sir.
And what else?
It was the pion minus plus the proton yields the neutron plus the eta 0.
Okay, so that is it. Okay, I was afraid I'd missed something when I was trying to.
I was wondering because I checked the baryon number and the lepton number and everything like that worked out. It was just when I came down to the energy on the right side of the equation, you have more energy on the right side than you do on the left side.
Gotcha.
That's what I was not, because the answer is that it's possible, but I'm not sure why.
Okay, so the deal is if the right side mass energy is greater than the left side mass energy, that's still possible. But if they were to tell you, for instance, that the pion and the proton were not moving, then it wouldn't be possible because it's got to get that extra energy from somewhere else. So what you'd have to have is if you came up, say, 1 giga electron volt short, the total kinetic energy must be at least 1 giga electron volt. That could be, half of a giga electron volt in the pi and half in the proton. But the main thing,
I didn't think about that. They could be moving.
Yeah, so okay. It can be done. It's just like I said, it has to be done with a certain amount of energy. So the better question would be if they say, is this possible if the total kinetic energy before the collision is blah, blah, blah? Then you can add that to the left-hand side of the energy.
Okay, that makes sense.
That's good. So you worked it out perfectly. That's exactly. But and everybody that hasn't worked this problem, notice he said he checked the conservation of baryon number. He checked the conservation of lepton number, because remember there's 3 of those. There's a lepton electron, lepton muon, and the lepton tau numbers. All of those have to be valid as well, at least in weak interactions. The lepton numbers do not have to be conserved in strong interactions. And remember, the way we differentiate those is the strong interactions cause decays very rapidly, and the weakest of forces cause them very slowly. So the strong interaction typically has lifetimes of 10 to the negative 24th seconds. The electromagnetic has on the order of 10 to the negative 16 to 10 to the negative 19 seconds. And then the weak interaction has on the order of like 10 to the negative 8 or even lower, or 10 to the negative 13th or even longer. Okay. So that's another thing to keep in mind. But that lepton number is kind of a weird one, specifically because the leptons do not partake of the strong nuclear force. They only partake of the weak nuclear force, and of course electricity and magnetism, and as well as gravity. But gravity doesn't come into play in this chapter. That's a lot of words, I know, but I'm just the baryon number is a set thing. You'll see that they also have strangeness and charmed and all that good stuff. Those numbers matter as well. Also, one thing I didn't hear you say, remember all the old rules are there too. You haven't learned 242 yet. You haven't had that course yet, but one of the first things you'll learn in 242 is conservation of charge is a thing. So you also have to add up the charges before and after. In this case, a pi minus and a proton, that gives you a -1 and a +1 charge, which add to 0. And then afterwards, you have a neutron and an eta 0. And the neutron and eta 0 are both 0. So conservation of charge is valid as well. But you also have conservation of energy and momentum. Yes, go ahead, Kobe.
I was gonna say, yeah, it was just everything, all the criteria that they give you worked out. It was just that one that I was confused on.
Yeah, that is the tricky thing. And they call it Q, which is better than delta MC squared because it's not final minus initial. It's actually the opposite. It's initial minus final, but it's delta MC squared basically, where you do initial minus final. and that's called the Q value of the reaction. If that comes out to be 0, it's possible. If that comes out to be positive, it's possible. If that comes out to be negative, then you just know the thing has to have some kinetic energy initially, and that kinetic energy must add up enough to make that negative back into a 0.
Okay. Thank you.
No problem. There's a one problem your book does like it, where it says, it said I think it was either the chi or the sigma minus was initially at rest. But from that one, you can actually work out, the Q works out okay, but from that, you can actually figure out what the kinetic energies and momentum of the particles would be after the collision. That's a very, very good problem, and you'll see it on the video from my N05 class on YouTube. It's also an example in the book. Anybody else?
No.
So you'll know the problem I was referring to was example 43.6 on page 1176. Example 43-6 on 1176. I wrote that down on this piece of paper, so let me let this person in and then show that to you. So someone else have another question? What I just concluded about this is Q can be negative where Q is M initial 1 plus M initial 2 plus ... minus M final 1 plus M final 2 plus ... times C squared. That can be negative, but then K initial cannot equal 0. Okay, and this was the example I was telling you guys to check out, 43-6, page 1176. Okay, I think somebody else was getting ready to ask another question, or maybe it was Colby. Either way.
I did have another question. This one was actually the next one. It was number 9 on chapter 43. They tell you the measured width of the, I'm not even really sure what that symbol is called. It looks like kind of like a pitchfork, sort of, and it has a 38686.
Yeah, a pitchfork pointing up.
Mm-hmm.
That's a
It's
psi.
about 300.
It should look like this.
Yes.
Yeah.
Kilo electron volts. I wasn't exactly sure how to do this one. I saw a formula online for it, because they wanted you to find the mean life for it.
Okay. State the whole problem for me kind of slowly so I can write down the information.
It says the measured width of the 3686. It has like in parentheses next to it 3686.
Okay, so they're saying M psi is equal to 3686, and it says MeV per C squared,
it just has it in parentheses. It doesn't say.
Okay, gotcha.
And it says the measured width is about 300 kilo electron volts.
Okay.
That's 300 kilo electron volts.
Oh, 300. Thank you. So you said the measured width is 300 kilo electron volts. And what did they say about this number? Did they just say psi with parentheses 3686 around it?
Mm-hmm.
Okay.
I think that's the rest mass, though.
Yeah, I would assume that's what it is, and it should be an MeV per C squared. What were they asking about it though?
What is its mean life?
What is its mean life? So the mean life, by the way, that's what we use in that's what we use in elementary particle physics or high energy physics, and it's really the half-life tau 1/2 divided by the ln of 2, which is the half-life divided by 0.693. So that's one thing I want to get out of the way. If they were to give you the actual, and that's what was concerning me, was this the actual half-life that they were saying? It's 3,686 seconds or microseconds or something like that. If that was the case, then you're just dividing that by 0.693. But what they're talking about here, this measured width, that's actually the in a curve like this, you have something that goes like this, reaches some maximum, and goes like this. If you go down half the height, so this is say h, and this is 1/2 h, and you measure that width, that's the width they're talking about. And if you look on page, let me see, try to remind you where this is at so you can follow up as well. I really need to see that question. I'll pull it up in a second if I can't figure out exactly what's going on with it, because I don't remember it off the top of my head. I don't remember doing it. It's in the resonance section, which I thought was 43.8. I'm not seeing that right now. No, it's not 43.9. There it is, 43.7. So if you look on page 1180, you see this is basically the number of interactions, and this is the energy. And that's normally what we refer to as width. But I don't see anything, I don't recall. I guess I could do it that way. So what we're going to say here is this right here is an uncertainty in the energy. And then, of course, remember the uncertainty in the energy times the uncertainty in the time is less than or on the average of or on the order of h bar, which is h over 2 pi. So what they're telling you here is that the width here is really a measurement of the uncertainty. It's about how long it actually lasts in some sense, or how much energy it could actually have. So we can submit that for delta E. And then we have, and I think that's what they're trying to get you to do here, is you determine the lifetime and say delta T is about equal to h bar over delta E. When you do that, that would be 6.63 times 10 to the negative 34th joule seconds over 2 pi. That's what h bar is. And then you divide that by, it said 300 keV. So I'm going to say 300 times 10 to the third EV times 1.602 times 10 to the negative 19th joules per EV. And that should give you what the half-life is, or excuse me, what the lifetime is. Now, let me double check and make sure I'm reading that problem right, because I can just pull up, I can pull up MyLab and Mastering for your course and check problem 9 and see the reading. Since you can read to share screen with us, so I can see it at a meeting at 10, but not until then. All right, so I'll take this one. And this is the chapter 43 homework, not the conceptual questions, I assume. Pulling it up, it's actually going pretty fast, so far. Wow, this thing's on fire. Sound like Adele. This thing is on fire. Boy, I got a good singing voice on. All right, I'm in, oops, wrong chapter.
Great.
I was hoping somebody laugh at my crappy singing. All right, now I'm looking at it. And you're saying it is problem 9, which I think is 43-34.
That was that's correct, because I think I ended up getting the answer from like just pure luck, because I think I did the formula wrong when I put it in when I actually was doing this problem. So I did end up getting 2. I'm still in the negative 21, but yeah, when I just did it the way that you said, I got 2.1. So I'm still in the negative 21. So
yeah, that should be.
That's right.
Yeah, it said the measured width of the psi 3686 meson is about 300 keV, estimated mean lifetime. So yeah, that should be just a application of the uncertainty principle for that particular problem. You say you did calculate that and got 2 times 10 to the negative 21?
Yes, sir.
Yeah, and that's the answer that's showing on here as well. So I was trying to look for a table. I want to see. I don't like them when they write stuff like that in parentheses without units on it. It drives me crazy. That particle core.
I looked on the table and there was only one other thing that had it in parentheses like that, and it was the rest mass.
Good
The
job.
rest.
Well, you did everything right, and that's cool. That's exactly what I would have done. Looked in the textbook to find something somewhat like it and see what they used it there. So that's exactly the way you want to do that. I don't see that particle though on the tables they have, so that's kind of a bummer, which I suspect is the reason they put that there. Yeah, I don't see 3686, and I don't see the psi particle anywhere, but it's probably in the table in the back of the book. But
there's one that they have on there that's like J over psi that's has in parentheses 3097 in the book.
Yeah, the J over psi part. Yeah, it's kind of weird. I didn't actually have a physics course on elementary particles. I had a advanced quantum mechanics class, but I did buy an elementary particles textbook, and it was actually upper level undergraduate, and I sort of worked through that. But that's about all the knowledge I have of elementary particles. I like it. It's kind of interesting, but it's got parts of it that to me are like what nuclear physics is, where it's sort of a some of it's like almost like curve fitting, in other words, and I don't like that aspect of physics at all, which it just means that there's certain parts you can't work out analytically as algebraic solutions and stuff. So, but again, that could be just my misunderstanding of the big picture of elementary particles, because I had no teacher actually teach it to me. Does anybody else have any other questions? And if they don't, it's okay for you to go for another one, Colby. Alyssa, Austin, Christian, anybody?
Doing the master lab right now while I'm listening.
Okay, no problem.
Yeah, so bye.
Okay, no problem.
The last one I had
Okay.
was the chapter was problem 11 on the chapter 43.
Okay.
It was like they wanted you to make a graph. It's kind of a long problem, but it's I got the second part of it, was just percent error. That part was easy, but I could not figure out the part A for.
Okay, I think I pulled the question up. It says, in a particle physics experiment to determine the mean lifetime of muons, the muons enter a scintillator and decay. Students have sampled the individual lifetimes of muons decaying with a time interval between 1 microsecond and 10 microseconds after being stopped in the scintillator. It is assumed that the muons obey the radioactive decay law, R equals R0 e to the negative t over tau, where R0 is the known activity and t equals 0 at t equals 0, and R is the activity in counts per microsecond at t. Here is the data. So they give you t versus r of t, make a graph of r versus R0, or excuse me, make a graph of the natural log of R versus R0. And from the best fit of the graph, do a straight line, find the mean lifetime. Okay, so let me give you what we're supposed to have on that. So we have R of t is equal to R0 e to the negative t over tau. If I solve this for R over R0, then I get just e to the negative t over tau. Now, if I take the natural log of both sides, I get the natural log of R over R0 is equal to the natural log of e to the negative t over tau. And of course, when you take the natural log of something raised to a power, the power just becomes the multiplier. So we'll get the natural log of R over R0 is equal to negative t over tau times the ln of e, but the ln of e is just 1. Okay.
I wasn't sure where to go from there because they don't tell you what R0 is.
Well, that's the beauty of it. You don't have to. all you have to do is plot R of t over R0, but R0 is a constant. So in this case, they did these time intervals. Basically, the closest you can get is R0 somewhere near that. Somewhere near the 55. I was saying that like you're looking at my screen. That don't help very much. So what you have to do is you just make a plot of R of t, and you can say R0 equals 100 or something like that if you really wanted to. Shouldn't really matter too much, but let me see. I'm trying to pull something up real quick. All right, make a graph of R over R0. So at t equals 0, it didn't give you that. Say, students have sampled individual lifetimes from between 1 microsecond, and they didn't actually give you that particular piece of data. Okay.
Because I was able to figure out like that R equal to R0 at time of 0, but that didn't really help me out very much.
Yeah. I'm trying to think of what would happen if. Well, here's an idea. You have R of t at t equal 1.5 microseconds, right? So you can plug in. Well, you can't do that because we don't have the tau yet. At t equals 0 seconds, of course, you just get R of t equals R0. I'm wondering what would happen if you just arbitrarily graphed not R over R0, but just R of t. I think that'll work, and I think all it would do is cause the graph to shift up or down by some arbitrary
doing that
amount.
on Excel, and I could not get.
Well, let's try it. Let's do this. I'm going to say, first off, I got an Excel spreadsheet open. So I'm going to share that with you guys.
Because I tried to make it like a straight line, and I could not get it to be a straight line.
Okay. So what we're going to do is we're going to put R of t, which if y'all can, actually, I might be able to see that at the same time. Yeah, I can see that at the same time. So well, good until my screen just blew up and did the whole darn thing. I hate it when Microsoft thinks it knows what I want to do. So t in seconds, or actually in microseconds, is going to be 1.5. Whoa. 1.5, 2.5, 3.5, 4.5, 5.5, 6.5. R, and that's of course in and I'm saying millisecond, but I really mean microsecond. Maybe it'll let me change that font of just that character to micro. Excel's like, man, you're asking me to do a lot. Oh, I'm crunching out so hard. Scrolling down to symbol and trying to remember my alphabet in real time. I'm like some kind of Mensa member for remembering the alphabet. Okay, so reactions per second, per microsecond. Now I got that done. So this was 55, 35, 23, 18, 12, and 5. So what I want to do is take the natural log of that. So I'm going to leave a little space here and say ln of R of t. Because again, I think it really, ln of r of t is going to be shifted a little bit by dividing it by r0, but I think it's just going to be a vertical shift. So I'm going to say this equals log, and I don't see natural log, but I think I can do log in the specifications of that. Will actually
I
allow.
think you can just type in ln, and I think it knows what you mean.
Does it do the ln? I hadn't done this. Oh yeah, there you go. So ln of this, and I copy that down to here. And now I'm just going to copy these, this whole thing right here as well. Okay, so now I'm going to take these two and do a plot. So let me make this window just a little bit larger. And I'm going to say data, or view maybe. It's been a little while since I looked at this. Insert, that's where it was. Stupid me. I'm going to do a scatter plot.
Is time going to be in the x or the y axis?
My memory is that the first column will be the y and the second column will be the x, but we will look at that and make sure. It appears that the 1.5 is in fact exactly where I didn't want it. So yes, you're correct. So let me do this. I'm going to insert column. I'm going to cut. I'm going to paste. I'm going to widen. Kill this, just because it's easier to do this than redo everything. I will do this. Yeah, I remembered it exactly backwards, but you guys been doing your lab, so y'all are much better at that than me. So scatter plot. Okay, and one data point really looks funny. Did I copy anything wrong? 6.5 and 5, is that the right data?
Yes, sir.
Okay, so it's not that great then. All right, so now what I want to do is I want to insert a trend line, which is not there, There it is. Trend line.
I think what I must have done is I think I took the ln of the time instead of the
Oh, gotcha.
the r of t, and that's what messed me up then. Because yeah, I see that now. That's going to give you the.
So I want to display the equation on this, and I do not want to set the intercept. And now I can kill this, and it looks like the slope of this is negative 0.4413. So that's why I was showing you all this. What we're plotting is y equals mx plus b, or y is the ln of r. Basically, remember the ln of r can be related to the ln of r over r0 by ln of r minus ln of r0. That's why I was going with the assumption that it's actually going to be just shifted a little bit. But when you put it there, you can see that that would be the change. And the slope is going to be -1 over tau. And then the x is just going to be the t, and the intercept should be 0. So I've got a slope equal to 0.4413, and that's negative, which we expected, and an intercept of 4.71. So B is, in reality, B would be, since I had ln of R0 negative on the left side, that could be the ln of R0. So you could actually get R0 from that as well. So B is equal to 4.7124. And the R value is 0.9639. So R squared is 0.9639. So I've got all that information from the graph. I want to stop sharing now and turn it over to my document. So what I was saying is the ln of R over R0 is just the ln of R minus the ln of R0. So if I put that on this side, which is what this is here, I could just add ln of R0 to both sides. And that would become the intercept. So if I raise the intercept to the, if I raise E to the intercept power, that should be equal to R0. And tau should be equal to 1 over 0.4413. That's 2.266 microseconds. Remember, it's microseconds because we put everything in microseconds. So that's what the lifetime should be. And of course, to get R0, we're going to raise E to the 4.7124. And I get 111.319. So R0 should equal 111.319, which you probably just call 111. So does that make sense?
Yes, sir. That makes sense.
Yeah, it's a neat problem. I like it a lot. I don't remember solving it before. It might be one they added new to the homework set this the last year or so. But yeah, I like it because it requires you to do some of the stuff you're normally doing in lab, which by the way, you can do with your calculator. And it's really nice and powerful to have something like that at your disposal in your pocket, as opposed to, we couldn't do anything like that in my days in school. We basically just had a scenario where we had to either go to a computer or we had to not do it. So see that, got that there. I'm just checking in everything, anything else I might have missed. There's this. And yeah, it's calling the answer 2.3, which is basically the 2 sig figs. That's what we got, 2.3 microseconds or 10 to the negative 6 seconds. And then it said the accepted value of the mean lifetime in muons is 2.19703 plus or minus 0.00004 microseconds. What is the percentage error of their result from the accepted value? So what you're looking for here is just going to do 2.3 minus 2.2 and divide it by 2.2, and you should get about 4.7%. All right, anybody else?
That was it for me.
All right, well, thanks for asking those. Anybody else have any questions yet? Remember, I'm not taking rolls, so you guys are free to go whenever you want to. But I'm going to
So we're not doing a lab today?
What's that?
We're not doing a lab today?
No, that's what I sent out the email about. The entire thing today is just a review. And it's mainly because I screwed up. I had a meeting that I missed, and now I had to reschedule the meeting for today at 10. So I'm trying to give y'all extra hours to, by offering other lab times as well as other times period, to make up for the missed lab time. And we may or may not do a lab next week. Of course, you should turn in your labs from any labs you have left. You should turn those in, but that's about it.
I didn't know. I didn't check the email. I got home from work real late.
No problem. Yeah, and I sent you emails for each of the labs. So we had one yesterday, we have one today, and we have one tomorrow at 1. And all of those emails include invites. So if you want to go to another one, you can go to the other one on Friday. And I might do something similar next week. I haven't decided whether I'm going to do that or whether I'm going to do the next lab.
Okay, thank you, Professor. See you at 12.
No problem.
So I just want to make sure I understood. So do we have a lab due next week?
No, the labs that were due from before Thanksgiving, they're due this week, and
Okay.
there's nothing due from this week to next week.
So like you're not assigning anything that would have been today.
Exactly.
Okay, that makes sense. Thank you.
No problem.
I'm trying
like
to think of a. Sorry.
Go ahead,
I
Chris.
think that was all for me. So I guess I'm gonna head out, Professor. Thank you.
Okay, no problem. Yeah, you guys are welcome to go. I'm gonna stick around here for a while longer so I can help anybody that might show up late. But like I said, you're free to go.
I'm trying to think of something that I can ask you. Can you do like an orbital velocity problem?
In what sense? Like one of the ones where it gives you the velocity at perihelion and they want to know what it is at aphelion or something like that?
Yes, that'd be
Okay.
great.
So yeah, the way that works is really it's conservation of angular momentum, and conservation of angular momentum says L initial is equal to L final. Now L is R cross P, and that's for point particles. Now, if you consider the size of the orbits of the planets, then the planets are definitely point particles with respect to that. The scale of the solar system is so bad that basically, if you zoom out or go high enough above the North Pole of the sun to include the orbits, to be able to see the orbits of even Neptune, you can't even discern Mercury, Venus, Earth, and Mars from the sun. It's not until Jupiter that you see a separate body unless you're using really good telescopes. So yeah, these things are really small. And the good news is at perihelion and aphelion, you have this scenario. So this would be aphelion, or excuse me, perihelion. It's like they make a pair, and this is aphelion. And you see at this point, the R and the V are perpendicular. And you see at this point, the R and the V, which I actually drew that one too long, the V at aphelion are perpendicular. So let me make this one a little bigger so it looks more realistic. The velocity is supposed to be much faster down here than it is over there. So let's say the perihelion distance, R perihelion for a particular planet is 3.4 astronomical units, and the aphelion distance is 10.8 astronomical units. And let's say the aphelion speed, V aphelion, is, let's say, I don't know, this is going to be crazy, but 30,000 meters per second. In other words, 30 kilometers per second. Okay. What we want to know is V at perihelion. So what you do, since R cross P, when they're perpendicular, just becomes R times P times some, let's call it direction vector. Okay. Which in this case is actually perpendicular to page, so it's really not relevant. So what we're going to do is we're going to say 3.4 times VP is equal to 10.8 times 30 kilometers per second. And from that, you can get VP is equal to 10.8 over 3.4 times 30 kilometers per second. So if I take 10.8 and divide it by 3.4, I get 3.167. Now multiply that times 30. And now I've got 95.3 kilometers per second. And you can see, of course, yeah, it gets a lot faster. That's why I chose the speed up here, so you can really see this speed out here is the slowest, and this speed in here is the fastest. And it comes from, of course, Kepler's second law, which says the orbits or the planets sweep out equal areas in equal time. Since this is going so fast, it might actually go from here to here in, say, 30 days. But since this one's so far away, for it to have an equal area, it must be a very thin slice of pizza. And you see that it only goes that far in 30 days.
Oh, I see now. Okay, that makes more sense.
Yeah, and that's what it is. And the cool thing is this gives you the right results for the Kepler's third law, which is harder to see. You know, Kepler's third law says the square of the period is proportional to the cube of the semi-major axis. That's kind of hard to see whether the closer planets are faster or slower, but it's this is completely consistent with this, meaning Mercury, which is closer to the sun, goes quite a bit faster than Venus, which is far from the sun. Even though the second law doesn't apply to that scenario, it's still a good tool to remind you, or a good mnemonic. So if you ever wonder that which ones are faster, just know the ones closest are fastest, just like in the case of a single planet.
Oh, okay. That makes a lot more sense now. Okay.
No problem. Reese, did you have anything? Or just basking in the physics glow?
I don't have any questions as of yet.
No problem. Like I said, I have time tomorrow, and this is going pretty good. Like last time, I waited around for another 30 minutes. I had another student come in, that sort of thing. So me offering this tells me I'm doing something decent. So we'll probably have the same thing next week, and in which case you'd be finished with your labs already. And this also gives me some more time to get the labs graded, which God, I hope they're done by this weekend. So anyways, you will definitely have your grades before you take your final exam. You will know what your position is in the lab, and therefore what your position is in the course by the time you take your final exam. So that's independent of whether we have another lab or not, but I'm just saying we'll definitely have it that way. So you guys, like I said, are free to go. I'm going to wait around here for probably another hour, or at least another 45 minutes or so. I'm going to get me some coffee right quick. I'll be right back.
Yeah, Professor, thank you for your time. It was
problem.
definitely a help.
Thanks, Christian. Appreciate it.
Yeah, I'm gonna start thinking of more questions to ask you if we do this again.
No problem. I'll be here right until just about 10. So if you need to come back, feel free. I just have a meeting at 10. That's why I'm leaving then.
Yeah, I understand.
All right.
Cool. Thank you.
Christian.